Okay, so in this video we're going to be looking at a couple of scenarios to do with Gaussian elimination. Okay, so the first example, or the first case we're going to look at, is going to be when we have the case where we have no solutions. Okay, so we're going to look at a case where we have no solutions, and the phrase that you might see is that the system is inconsistent. Okay, the system is inconsistent. Okay, so that's going to be our first case. Now, rather than explain what this is, we'll just consider an example first, and then we'll work out why we end up with this. Okay, so let's consider the system of equations. We've got 2x minus y plus z equals 1. We've got 3x plus 2y minus 4 lots of z equals 4. And we've got minus 6x plus 3y minus 3z equals 2. Okay, so that's going to be our system of equations. Okay, so first thing we'll do is we will put into our matrix, so using our coefficients, it'll be 2 minus 1, 1. Then our solutions after it will be 1 for the first line, first row I should say, and then it'll be 3, 2, minus 4, and then at the bottom, 4 in the solutions part for row 2, then negative 6, 3, negative 3, and 2. Okay, so I get this here. Right, okay, so our first thing we're going to do is we want to try and get our zeros, if we were solving this, in our bottom left corner. Okay, so let's focus on, say, this corner here. We want to try and get zeros in this corner here. Okay, now we've done this a few times, so we can do a couple rows at one time now. Okay, hopefully we can start doing this. If you're not comfortable, just do them one at a time. Okay, but let's just deal with this first column. So I know I want to get row 2 to have a 0 where that 3 is there, and I want row 3 to have a 0 where that minus 6 is here. Okay, I'm going to bounce them off row 1 to do that. Okay, so let's think about how I get a 0 in row 2 there. So I'd have to do 2 lots of row 2 minus 3 lots of row 1. Okay, so we see that's how I get a 0 in that entry there, yeah? Now also I can do row 3, okay, so I want to try and get a 0 where that negative 6 is. Therefore, I'm going to do row 3. Again, I'll bounce it off row 2, but I want to add 3 lots of row 1. Okay, I'll bounce off row 1, I should say. So I'm going to add 3 lots of row 1. So you see how doing these operations, I'd be able to get zeros in those 2 entries there, yeah? Okay, do you see how I've managed to get those there? Excellent. Okay, that means if you start seeing that, you can speed up the process doing maybe 2 at a time, okay? If you don't rush it though. Okay, I'd rather do it 1 at a time and got it right than rushing it, okay? So let's do that. So row 1's going to stay the same. And, okay, let's now do row 2. So row 2 is 2 lots of row 2, take away 3 lots of row 1, so I'm going to get a 0 there, that's what I wanted. Okay, 2 lots of row 2, that gives me 4, take away 3 lots of negative 1, that's really adding 3, so 4 plus 3 is 7. So that's 7 there. 2 lots of negative 4, take away 3 lots of 1, so 2 lots of negative 4 is negative 8, take away 3, that's negative 11. 2 lots of 4, that's 8, take away 3 lots of 1, so 8 take away 3 is 5. Okay, so I've got that as my second row there. You okay with that? Right, last row. Okay, row 3 plus 3 lots of row 1. So if I add 3 lots of 2 to negative 6, I'm going to get negative 6 plus 6, which is 0. Okay, 3 plus 3 lots of negative 1. Okay, so that's 3 plus negative 3, which is 3 take away 3, which is 0. Negative 3 plus 3 lots of 1, that's negative 3 plus 3. That gives me 0 again. 2 plus 3 lots of 1 is 2 plus 3, which is 5. Okay, so I've got that last row there now. And you'll see something different happening to what we've seen before. Okay, now let's look a bit closely at what that row 3 now is. And this is the reason why we've got inconsistency. Okay, It's inconsistent here, inconsistency, because what row 3 is telling us, okay, so from row 3, it's telling me that, well, 0 x's plus 0 y's plus 0 z's has to give me the value 5. Yeah? But if I don't have any x's or any y's or any z's, in other words, I've got nothing on that left-hand side, then it can't equal, according to my row, it equals 5, but that isn't true, is it? Okay? Okay, impossible. So therefore, the system's broke down. Okay? So what we say is, there are no such values for x, y, and z that solve this system therefore we have no solutions. Okay, so you can see that our systems broke down. Yeah, that last row gave us something that was impossible. It can't happen, it broke down, therefore there was no solutions for x, y, z that would have solved those equations there. Okay, so do you see how nothing really changed for our steps? We're still in Gaussian elimination to get that step there, but just it gave us something that we could then no longer solve. We've got no solutions. We're okay with that? So if it talks about no solutions, or if it talks about inconsistency, okay, then that's what it's meaning. You're going to end up with a row at the bottom that you're going to have no x's, no y's, no z's left, okay, equaling something non-zero, okay, therefore it can't be true. Alright, because the only thing that would make this true is if it was 0 there as well. Yeah, because you could have nothing on one side equals nothing on that side. That is true. We okay with that? Okay, so that's the first case we can get, is we can have something that's no solutions, okay? The second case we're going to look at, okay, is when you actually get infinite solutions. Okay? So in other words, we can have more than one solution. Okay? So, again, we'll just go straight into an example to see how this works. We're going to solve the equations x minus y plus 2z equals minus 3. Just to let you know, sorry, I should also say infinite solutions, the code word for it as well, sometimes exam questions say, is redundancy. And you'll see why in a second, okay? Redundancy or redundant, okay? So that's what you might see in a question, and that's what you're thinking about infinite solutions, okay? So we're going to solve x minus y plus 2z equals negative 3. We've then got 4x plus 4y minus 2z equals 1. And we've got minus 2x plus 2y minus 4z equals 6. Okay, so that's what we're asked to solve here. So again, the starting off point is we still treat it like normal Gaussian elimination. Okay, we're going to create an augmented matrix and we're going to insert our coefficients. Okay, so we've got 1, minus 1, 2, minus 3, 4, 4, minus 2, 1, minus 2, 2, minus 4, 6. Okay, so that's what I've got to try and solve here, that augmented matrix. You okay with that, folks? Right, okay. So let's look at how I want to. So again, I want to try and get zeros in this bottom left corner, but we'll start off with the first column. So I want to try and get that 4 in row 2 there to become 0. I want to try and get that negative 2 in row 3 to become a 0 there too. Okay, so let's see how I would do that. Well, start off with row 2. I could do row 2, take away 4 lots of row 1. Do you see how that's how we'd get a 0 for that entry there, yeah? Yeah. Cool, okay. Row 3. Okay, how would I get a 0 in row 3? What would I need to do with row 3?
Plus 2 R1.
Yep, plus 2 lots of row 1. Okay, so row 3 plus 2 lots of row 1. Okay, and you'll see that that's what we cancel there. So let's do those and let's see what we get. So, row 1 doesn't change. Right, let's add, so let's subtract 4 lots of row 1 from row 2. So I'm going to get a 0 in that first entry. 4 take away 4 lots of negative 1. Okay, that's going to be 4 lots plus 4, that'll eventually be, that's going to be 8. Negative 2, take away 4 lots of 2, that's negative 2, take away 8, which is negative 10, I believe. And 1 take away 4 lots of negative 3, so I'm really adding 12 onto 1, which gives me 30. Okay, so that's what my row 2 looks like. Okay, 0, 8, negative 10 and 30. Okay, let's look at row 3. Okay, so I'm going to get a 0 in that first entry. Let's add 2 lots of row 1. Well, 2 plus 2 lots of negative 1, that takes me back up to 0. Negative 4 plus 2 lots of 2, that's negative 4 plus 4, that gives me 0 again. And 6 plus 2 lots of negative 3, that's 6 plus negative 6, which gives me 0. Okay. Now you're going to say, well, this is very similar to the last case, but there is a difference. The difference is that last row is true. Yeah? 0x's plus 0y's plus 0z's would give you 0. So there's nothing mathematically wrong with that. But it's not giving us any information here either. It's not telling us anything that we want to know, because we ideally want to try and find z in this case, in the bottom row, okay, row 3. So what we actually have here is we have a redundant row. It's a row that's not really telling us anything. Okay, we've got a redundant row, redundancy. Okay, and that's why it's code for infinite solutions. Okay, so how do we get our solutions now? Well, we still can solve this. We've not done anything wrong. There's nothing mathematically wrong with that system. It just means we've got to work harder to get what our solutions look like. So what we need to do is we do the following. So let's write a wee note for ourselves first. So if we look at row, which is row 3, look at row R3, then everything has been cancelled. So we are only dealing with 2 rows. Okay, R1 and R2. Okay, they're the only 2 rows that have got any sort of value to them. Okay, so what we need to do, so as we have 3 variables, okay, x, y, and z, and only 2 equations left, then we need to set one variable as a parameter. Okay, so if we do that, then we can get the other 2 variables in terms of that parameter as well. Okay, so we won't actually get a physical number out, okay, but we have to set it and get in a sort of what you'd call a condition on the other 2. Okay, so let's start off with z. So we normally let z be the first thing we find in a system. So let's let z equals alpha. Okay, some number alpha, and alpha is in the reals. Okay, the real set of numbers. Okay, so what we can now do is now go from row 2, we can now get a condition on what the y would be. Okay, so row 2 is telling us that 8y minus 10z equals 13. Okay, well, if I rearrange that and I substitute alpha in for z, I'm going to get 13 plus 10 lots of alpha. Okay, therefore the condition on y would be 13 over 8 plus, well, 10 divided by 8 is 5 over 4 lots of alpha. Okay, so that's a condition on y. If I knew what z was, if I knew what the parameter z was, I would then substitute that into this y condition here. Okay, does that make sense so far? Right, okay. Then I can now go to 1, 1. So from row 1, well, what have I got? I've got x minus y plus 2 lots of z equals -3. But substituting what I've got, so that's x minus y, so minus 13 over 8, minus 5 over 4 alpha, plus 2 lots of z, that's 2 lots of alpha, equals -3. Okay. So if you take everything over to the other side, okay, so you end up with -3 minus 13 over, sorry, plus 13 over 8, minus 2 lots of alpha, plus 5 over 4 lots of alpha. Okay, so that's what I'll just put everything on the other side so I can get x. And if I can combine the bits that I can combine, so I can combine -3 with 13 over 8, that would give me -11 over 8. And I combine my alphas, -2 alpha plus 5 over 4 lots of alpha, that gives me -3 over 4 alpha. Okay, so why this is known as infinitely many solutions, we've got conditions on x, y and z, but all in terms of alpha. Okay, so solutions then, well, x was -11 over 8 minus 3 over 4 alpha, y was 13 over 8 plus 5 over 4 alpha, and z is alpha. Okay, again with alpha being in the reals. Okay, so we've got our solutions, it's just all in terms of a parameter alpha. So if alpha was 1, we substitute 1 into them, we'd get ourselves a value for x, y and z. If alpha was 2, we'd substitute that in, we'd get another solution for x, y and z that would work. Does that make sense? Anybody got any questions on that? Okay, thank you.